All right. So welcome back to next lecture. So in this lecture, we will discuss about the DC machine operation as a generator and motor. Generator and motor operation. Just we would like to see the key important things about the generator and motor. So in generally these machines, whether it is generator or motor, consist of one rotor part as we represent schematic view of that as A and AA terminal, in which so the induced EMF will be EG. This is internally generated EMF, and internal resistance of the armature we represent as RA. The amount of the current produced by this armature is IA. These are the common whether it is generator or motor. But the current direction may be reversed for the motoring action. In generally, in construction wise, these are the common things. So instead of that, let me not to represent the direction of the current here, as because the heading is generator and motor. So apart from this, we also have field winding on the stator, and field winding terminals we usually represent with FF or F1, F2. If the field winding resistance is RF, so the current flowing through the field winding when we apply a DC voltage across the FF is IF. This causes the flux inside the core of the stator. As a result, when this rotor rotates by a prime mover torque T, suffix prime mover, then this machine try to rotate in clockwise direction at a speed of n rps revolutions per second. And one thing you try to observe carefully here, that so when the machine is rotating as like this, if it is operating as a generator, we need to provide the mechanical power as a input to this shaft in the form of prime mover torque. And when this torque is acting on the armature try to rotate inside the magnetic field provided by the field winding. As a result, induced EMF is developed. Let me put these things in the wording form for better understanding. Initially, what are we doing? We are providing the prime mover torque to whom? To shaft. This we are providing at the shaft. As a result, the armature, the armature rotates rotates, let us say, at n rps revolutions per second. Once the armature rotates, so where does this armature rotating? Inside the magnetic field. Inside magnetic field. Who is producing this magnetic field? Stator wind, which is field wind, magnetic field. Let us say phi. If you want more specifically, you can represent as phi s, stator field flux. Stator field flux, we know from the Faraday's law, when a conductor cuts the magnetic field, then the conductor induces the EMF. This process will induces EMF where in rotor conductor, in rotor conductor. And we had seen these things also in detail. Just refer back if you have any doubt. This induced EMF E is equal to, the generalized formula is BIL, BIL. So this is maximum induced EMF. As the flux density also change sinusoidally, means like flux is changing something like a let us say trapezoidal form. So we would like to take, that may not be pure sinusoidal, remember that. So we would like to take the average flux density under one pole, and current per one parallel path we would like to take, so that b, sorry, so just I made small mistake here. So just this will not be the induced EMF will be generally so B L V if the conductor is rotating at a velocity of V. So if this is rotating at a velocity of V, so the induced EMF generalized formula is BLV. So this we derived new formula that by taking the average flux density B and L is the length of the conductor and V is the velocity of the conductor. So when we take this and when we simplified this, we observe that this is equal to Pz by A into flux into the speed. And this expression also can be written further that Pz by A into flux into capital N, where N is in RPM. And if you make this to be as like similar to the let us say torque formula, we can make one more change also here that so this speed can be expressed in terms of the let us say rotational speed, angular speed. So as like this Pz by A, this constant. So what I will do is that I will divide with 1 by 2 pi and multiply with 2 pi. So here we will get 60 when n is in RPM, revolutions per minute instead of RPS. So I will multiply and divide with 2 pi. So this flux phi will be there. Apart from that 2 pi n will be there divided by 60. So this 2 pi n by 60 we can write as angular speed, which is equal to 1 by 2 pi. So P z by A into flux phi into angular speed omega. So this angular speed omega we will write radians per second. Radians per second. So this just try to have an idea that the induced EMF EG, so the capital induced EMF, this may be RMS value, let us say EG is equal to this much. So when we consider inside the machine for a generator, so try to just get acquainted with these relationships. So depends on the requirement, we may use any one. Preferably we choose this one or this last one or this middle one in that order. Now, one thing you try to observe, fine, we got the induced EMF in a coil, but when this armature is connected across the load, as long as this things takes place, no issue. But here, one like very interesting observation you need to make here that when when the armature AA terminals, AA, what is AA is armature. Armature is connected with load, is connected with load. Now you can observe a new phenomena. What is that phenomena? Is that the armature conductor carrying a current of I amperes, carrying a current of a current of let us say IA by A amperes. We know that so there are several number of parallel paths in which each parallel path current is equal to each conductor current. So let us say this is the current, and what we know usually is that when a conductor carries the current in this way, and let us say in terms of the coil form, so as like this, what is going to be happen that you need to observe. When a conductor carries current, then it tried to produce the magnetic field around the conductor. This you need to observe. So as long as load is not connected, no current flowing through the armature conductor. But once the load is connected, current is passing through this armature conductor. So according to right hand thumb rule, this is the direction of the flux in the side 1, whereas in side 2, you see that this is the just apply the Fleming's right hand thumb rule. So this is the direction of the flux. Now try to observe that very carefully. There will be flux established around this conductor. Now again you can have some kind of these things that, so let me say this flux lines will be downwards as like this. See here, so this conductor is downwards inside the coil, here also downwards, and these flux lines will go, half of the flux lines in this direction, remaining half of the flux lines will try to pass on the top of this. This is the flux pattern established by this coil. Now try to observe what is going to be happen. So see here, wherever flux lines are emanating, so one will become north pole, other will become south pole inside the core. So here it will become north pole, as because the core is emanating here, there will be core, actually it is enclosed with that. This becomes the south pole. This becomes the south pole. Now see that flux is in downward. Let me put here that, or let me take same color. So the flux is in downwards, that means flux density is in downwards, this is B. So next, what is the current direction for this left side? Side 1, this is what the side 1, this is other side is the side 2, side 2. Now for side 1, what is the current direction? What is the current direction? It is into the board. So let me put that current direction as into the board as like this. So now we would like to see what is the force experienced on this conductor. So for which, so let us apply now Fleming's left hand thumb rule. Fleming's left hand rule. Left hand rule. And see that place the, so thumb, forefinger and middle finger 90 degrees to each other, and in which the, we said several times, this is following the FBI rule. FBI rule. So whether it is left hand or right hand, so now left hand rule. So place the forefinger along the flux direction and the middle finger along the current direction. So let me write here for your sake. The current represents the middle finger, this I said several times. This is what the forefinger, and thumb represents the force acting on the conductor. So this is what the force or torque, it's your wish. Now see here, so place yourself, just try to work on these things and you will come to know the middle finger, which represents current, is going into the board or into this paper, and the forefinger try to represents downward, downward, downward. Then what about the force? How the force is going to be act on the conductor is, just try to inspect that. So if these are the things, so the force acting on this conductor will be in this direction. Let me choose different color. So this you need to work on this, these basic principles. This is the side 1. So the force will be in this direction. So how should I show is that this is inside, this is okay. So then it will look like this. It will look like this. This is what the force. But actually, so when we strictly speaking, so in 3D view you have to imagine. So if it is in, so then right. So this look like downward some extent like this. This is what the force. So the force acting on this conductor will look like in this direction. Similarly, you can inspect same thing for side 2. Same thing, this law for the side 2. So for side 2, this force will try to act on upward direction. So now as a result, see that just same concept you try to incorporate here, how the machine is rotating clockwise, how the prime mover torque is acting clockwise. But what about when load is connected, immediately an opposing force is developing on the armature. As a result of this, that try to retard. But if we provide more amount of the prime mover torque, then it try to rotate. So we need to provide, once it is connected to the load, once armature is connected to the load, we need to provide more amount of the torque. Why? Because there will be an opposing torque which we call that as a electromagnetic torque, TEM, electromagnetic torque, or simply TE. So where TE is opposite to the prime mover torque. But what is the main torque which helps for rotation of this armature in clockwise is prime mover torque. So what is the opposing torque here produced under generator case is that the electromagnetic torque. So TEM torque, so which is basically force into distance. Once you have this force and how much is the conductor length, so that gives the torque. So let me say directly, this is a TEM, electromagnetic torque. So this force, when you try to write in terms of the torque, it try to give in this way. This is only side 1 I had shown you here. You can take the side 2 also and you can work on that, and how the force is acting on this conductor you will come to know. So this TEM is acting on conductor, on coil, let me say on coil, such that such that it opposes it opposes it opposes the prime mover torque TPM. It opposes the prime mover torque TPM. This is very important observation. Thereby, 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 so the machine will come to halting position if I won't provide any extra torque. So when load is connected, the machine will demand more amount of torque to overcome this electromagnetic torque. This electromagnetic torque is internal phenomena, just like cause and effect. If you are trying to put one torque in other side, one side, let us say clockwise, somebody try to act in opposite side when load is connected. In order to still rotate the machine in the same direction, you need to provide more amount of the electromagnetic, prime mover torque. This is for the case of generator. Now, the similar but little opposite kind of features going to take place in case of motor. Let us see that. So, very interesting, and see here for case of the motor operation. The previous thing what we discussed is the generator operation. This is all things about the generator. generator and these are very important crucial points to understand the difference between motor and generator. So let me take again the same armature as like this, armature terminals, as like this. I will not say what is this armature voltage as of now. So there will be a field winding and whose terminals usually we call FF, and this may be applied across some voltage and it may result some field current, and as a result field flux is produced, right? So now we already said several times, motoring operation means we will be giving electrical energy as an input. We are not going to connect here load. Instead of that, we are trying to connect the power supply here. That means we are connecting a source. What kind of machine is this? DC machine. So I should connect a source across this. So this is, let us say, source voltage Vs, and this source is supplying current Is to the machine. Or if you want, just instead of writing every time Vs Is, just I'll say V and I, which is the input. Now we connected this across the armature. So we know that armature has armature resistance. Now think in general way that, so how much is the power fed to this machine? The power input. What is the nature of the power input? Electrical power for motor. What is the output? Mechanical power. So like this here, this is what the shaft going to rotate. There will be certain torque and speed produced by this shaft. This can be utilized for some external mechanism. Now let us understand clearly that what will happen in this way. Now let us assume our machine is rotating in, so let us say counterclockwise direction. So the rotation of the machine is n rps, or the armature is rotating at a velocity of v. And as like the, let us say, uh, generator case, so what we see here in case of the motor is that, so we usually have coils, let us assume same thing here, and if the machine is rotating in this direction, or let me say, in some extent in this way, that here some north pole is there, stator north pole, here stator south pole is there, and we know that the current will be coming out of the north pole and current is entering into the north pole. In that direction I am considering this current is flowing. Just try to understand this word, very important. So these N and S are the stator north and south pole. Under the north pole, so the current is coming, going into this board, where here current is coming out of the board. Now, if the machine is rotating in counterclockwise direction, so remember that here little bit different operation, that the amount of the torque produced by this armature on the armature we call as electromagnetic torque, TEM. Reverse. Previously we have prime mover torque, from which the opposing force is electromagnetic torque. Now, electromagnetic torque is helpful for rotation of this armature in counterclockwise direction. So, that electromagnetic torque is acting on this conductor in downwards. So, just let me say directly here instead of making much more complex, that electromagnetic torque is acting in counterclockwise direction like this. But whenever I will connect some load over here, some mechanical load, let us say, some big, let us say, sugarcane machine, so where we need to rotate some gear mechanism by this shaft of the motor. So once we switch on the machine, once we insert some sugar canes inside this, then some load will be applied. As a result, there will be load torque generated which try to act opposite to the electromagnetic torque. Just understand up to this extent, that so that inside mechanism how this electromagnetic torque is quite opposite to the load torque. So but in generally, for a motor, the electromagnetic torque TEM is responsible for for rotating for rotating rotating armature 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 in in counterclockwise direction or anti-clockwise direction. Anti-clockwise, the machine may rotate clockwise also, but here I considered counterclockwise for generator clockwise. So that is the convention I adapted. Once this is taking place, when load is connected on the shaft, when mechanical load, here when load is added on the shaft, on the shaft on the shaft, then 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 a load torque TL, a load torque TL will will try to act on the shaft, on the shaft opposite to opposite to the electromagnetic torque. So this load torque is equivalent to prime mover torque in case of the generator. See, the entire operation is reversed previously. So just for sake of understanding, just I am stating this point, you no need to make clearly that it is equal to prime mover torque. Just imagine this load torque is equivalent to prime mover torque TPM. Now you can make just complete reverse operation of the generator as a motor. See here, if I'll give the prime mover torque, rotor going to rotate, it going to induce EMF. Once it induce EMF, when we connect the load, then current is flowing through the armature conductor, that is producing the electromagnetic torque which try to act opposite to the prime mover torque. This is for generator. So now reverse. See here, once see here, once source is connected, the conductors are carrying a current of I amperes, then which are placed inside the magnetic field. Then once let us assume that that is experiencing that this armature power, which is equal to armature voltage into current, is acting, means converted into torque, electromagnetic torque. That we said, what is the electromagnetic torque? Is interaction of the stator field flux and rotor field flux. As because rotor is also carrying current, now see, by the applying this source, and stator field is already there, rotor field is going to produce when I connect the source. These two will interact and produce the TEM. The TEM will act on the rotor conductor. Now try to observe, when rotor conductor is rotating, then this shaft going to rotate. If we add any load on this shaft, that will try to produce an opposite torque to this electromagnetic torque, that we call as a load torque. Now see the real phenomena. This is very important. Just let me state clearly here. Observe very carefully, listen very carefully this point. As long as rotor conductor carries the current, no issue. So this is placed inside the armature. Let us say armature is under stationary. That means conductor is under stationary inside the magnetic field. Let us forget whether it is carrying current or not. It doesn't matter. Now let me state this in this way. If rotor conductor, if rotor conductor rotates in stator magnetic field, in stator magnetic field, in stator magnetic field. So what is going to be happen? See that if a conductor rotates in stationary magnetic field, according to Faraday's law, it induces EMF. EMF is induced in armature. But this is not a generator. We cannot call this is generated voltage. As because this is motor, in motoring action also induced EMF is developed. So this induced EMF in motoring action, when a conductor rotates inside the magnetic field, then it induces EMF. This induced EMF we call as back EMF. Back EMF. We usually call this, represent this as E suffix B. The expression for this back EMF is same as that of the generated EMF in case of the generator. So this is very important word, so you should understand clearly. So it produces back EMF. Now I would like to state in this way. What I will say is that, so what Faraday stated, if a conductor, just let me say in short form that if a conductor rotates inside the magnetic field, it induces the EMF. Let us say in this way, if this conductor rotates inside the magnetic field, then it induces EMF, something like plus minus. EMF is produced. One thing. Or let me say a little bit just more precise way here. Just conductor, no current carrying conductor. It doesn't matter whether it is carrying current or not. So this is the statement. What I'll say is that if conductor rotates, if conductor rotates inside magnetic field, inside magnetic field, magnetic field. So these words are very important. Just try to understand. If conductor rotates inside magnetic field, according to Faraday's law, this produces EMF. One thing. This is for which case I will give you. Just wait a second. In other case, one more thing is taking place. What is that? Is that a rotating conductor is carrying a current of I amperes. If a rotating conductor is carrying a current of I amperes. So, if a rotating conductor carries a current of I amperes, around the conductor it establishes the flux. And as a result, when a conductor establishes the flux, just try to understand in this way. So the conductor will will experience a force called as Lorentz force, so which is equal to BIL. So this force will try to create some torque. So see these two things. So I am not talking about the specific generator action or motor action. Just what I am saying is that if a conductor rotates inside the magnetic field, it induces the EMF. If a current carrying conductor is there, it experiences some force. So now try to see, let us think of whole generator part. Okay, once generator is connected with the load, this point onwards you continue. Once armature is connected with the load, what action is taking place actually? As long as load is disconnected, no current is passing through the conductor. But once load is connected, the conductor is carrying a current of I amperes. When conductor carries current of I amperes, immediately this action going to take place. That means some force will try to act on the conductor. That force will try to develop as a torque, which we call as electromagnetic torque in case of generator, which try to act opposite to the prime mover torque. We had seen more clearly with the help of various principles how the opposite torque is produced from the Fleming's left hand rule. Fine. So next is, in case of motor, see that as long as power supply is connected, so the armature is means have carrying a current of I amperes, but still let us assume machine is not rotated. Then this armature will try to produce some magnetic field, which we call as rotor magnetic field. The interaction of this rotor magnetic field with stator magnetic field try to produce some torque on this rotor. Once torque is acting on the rotor, rotor try to rotate. Who is causing this rotation? Electromagnetic torque. Once rotor is trying to rotate, these conductors also rotating. Where does these conductors rotating? Forget about whether it is carrying current or not. It doesn't matter for me. Is the conductor rotating or not? This conductor is rotating inside the stator magnetic field. As a result of that, see that if a conductor rotates inside the magnetic field, this induces EMF. So this induced EMF we call as a back EMF. These are the very clear and clean important differences between the motoring action and generator action. So this part of the differences is very important to understand. Okay, so right, so this is all about the motoring and generator action. Now let us see some more details about the power flow, so that we can understand more clearly the motoring concept. So we already discussed about the generator, so that we named. Let me put here once again that block diagram, if or let me take only motor, so as because time is also important. So for motor, what is the input? Electrical energy or power as the input. I'll write I by P input. So once I'll give electrical energy as the input, so now try to see in case of motor what are the things going to take place. So this is in case of here I used V and I symbol, so I'll call this as P in is equal to Vi. P in is equal to Vi. See, I applied a voltage of V, DC voltage, and a current of I amperes. So, sorry, so I took this slide over here. So let me take this. So, or let me cut this and let me delete this slide. So I should take below this. Fine. So right. So okay, so now let me paste that. Fine. So now we are giving electrical energy as the input. So see how much is the voltage V, how much is the current I. This is the input. Now once that input is given, immediately what portion we would see here? See that once current is passing through this armature, now in which direction current is passing? Previously, like from armature to the other side, terminal side. Now from terminals to armature side, this is what motoring action. Power flow is reverse. Power flow is reverse. So now this is Ia. Then immediately armature resistance is there. So Ia square into Ra loss will be there. So that loss we called as copper loss. That loss we called as copper loss. So immediately the copper loss take place. So how much is that? Ia square into Ra. If it is a separately excited, only Ia square into Ra. If it is shunt excited, Ia square into Ra plus If square into Rf. Both will be there. Next is, if we subtracted this amount of loss from the input, the left out power is what? Reaching to the armature. So the power in armature. I will not say developed power. Why? Because armature is not developing this power. Just this power we got from the external source, that is some battery. So how much is that? If E is the induced EMF in the conductor, which we call as EB into Ia. EB into Ia. EB is the back EMF. Back EMF. And what is its expression? Same as like the generated EMF. Instead of EG, I am using EB for the motor action. That's all. So PZ by A into phi into N. I said this expression we frequently use it. So then after this portion, the power flow stage, the next stage is that, see here, so there will be some more losses. What is going to be happen is that this EB into Ia will try to develop a electromagnetic torque, TEM. TEM. This electromagnetic torque will rotate the entire armature. Once armature start rotated, then there will be some frictional and windage losses or all constant losses, iron and core losses. Let me call that as a stray losses. What are the stray losses? Stray losses are magnetic and friction and windage losses. That is core losses. Let me write here. Stray losses are iron or core losses. Both are same. Core losses plus friction and windage losses. I dealt about these losses previously, just refer back once. Then once this is gone, once I'll subtract this amount of the losses from the armature power, EB into Ia, then the left out power is what we call as mechanical power. Mechanical power. Mechanical power. So this can also be called as shaft power. Shaft power. Why? Because this power is developed on the shaft. So we can call this as a shaft power, or we can also call this as sometimes gross mechanical power. Gross mechanical power. Orally, how much is the power output? Is this one. So here also we may get some amount of the torque that let me tell you little later. So this is the power stages in a motor. Power stages in a motor. Just reverse diagram we had seen for the generator. How? Initially the mechanical power, that is the prime mover output, stray losses followed with power in the armature developed, then copper losses, then electrical output power, like that. Just reverse diagram we had seen. So now once we know this, so now let me discuss some more details about the torque, different kind of torques here. Usually you should understand this torque very clearly. So see here, so this generally you should understand from the mechanical subjects that the torque is equal to force into force into force into, let us say, distance. Force into distance. For example, if I'll have some circle kind of object which we call as pulley, so this is pulley. So we want to rotate this. So this is called as a pulley, pulley, and we want to rotate. Let us say its radius is r. Its radius is r, and I want to just, let us say, a force is applied on this in this direction. This is the force. Then if this force is applied in that direction, it's going to be move in linear way, but what I need is that rotational speed, like this. Let us say n rps, revolutions per second, I need. Then what we do is that this force into distance, what is the distance? Is circumference of this pulley. So that force f into the distance is 2 pi r, circumference is 2 pi r. So this is what the force or the torque which is acting on. Sorry, just one second. One second. Yeah, fine. So this is what the generally we can call this as work done. Also, let me write that. Why? Because we would like to relate this to the power. I will tell you how. So work done by this force is equal to force into this distance, which is equal to 2 pi r. This torque can also be expressed in this way, that so the work done is equal to this much. Now the power developed is equal to the power. So I hope something is missing, just let me clarify this. So one second. Right. So just let me remove this. Let me make clearly first this force into distance. That distance is this radius basically. Force into the distance is r, and what is work done is that work done is equal to energy. Work done by a force, by this force, let us say, by this force is equal to, so some, yeah, so work done by this force is equal to, so force into just both expressions are becoming same. So then just let me remove this uh, or just instead of these all mechanical terms, let me make in more simple way that, so what I would like to say here is that the or let me relate this torque with the power directly, this in this way. So the developed the power developed is equal to, just try to understand that, torque into angular speed, torque into angular velocity. Just refer back that how the power developed is equal to torque into angular velocity, so that you will see in the like mechanical subject these things. So anyhow, so this is the power developed which is related with the torque into angular velocity. And this torque, let me say, the armature developed torque or the electromagnetic torque TEM into angular velocity, we can write as 2 pi n by 60, where n is in rpm, revolutions per minute. If I will use a small n, I will write 2 pi n. So that is the generalized principle. And here this power, let me say p, let us say p a, armature power, just to get more clarity. So this is what the pa, the power in the armature is equal to eb into ia. EB into IA. You can carry forward the same notation. Then once we know this, then it is easy to find the required power or the torque. We usually take this kind of expression. So if I want the TEM can also be called sometimes as TA, armature torque for the motor, is equal to the armature power divided by omega, where omega we can write as 2 pi n by 60. So this also is useful expression for calculating the problems. And now try to observe in this expression, if I'll use just generalized way, try to understand here. If I'll use this power as armature power, then I'll be getting the armature torque TEM, which is electromagnetic torque. But if I'll use the shaft power, then what torque I'll get is the gross torque or the shaft torque, TSH. So this I'll call as PMECH, mechanical power. So now let me write this PMECH, same principle. The power is equal to torque into speed. So this TSH into, so 2 pi n by 60. 2 pi n by 60. So you can use even this expression also sometimes, so to calculate the things. So remember one thing, that this shaft is the gross torque or the final torque, so on the armature, the final torque on the armature. So for which let us take one problem and let us wind up this session here. So just simple problem, let me take here as like this. So this is one example, just I'll be giving data. A DC motor takes an armature current of IA is equal to 110 amperes. The armature current, how much it takes is 110 amperes. So if you don't want to represent this IA, so let me represent as I with respect to our previous diagram. So let me take this diagram here. This is what the DC motor. So IA is equal to I, that if you want you can use that notation or just simply you can discard that. So this is what the reference diagram, just to get where is IA, what are the things. So a DC motor takes IA of 110 amperes at some voltage, let us say V is equal to 480 volts. 480 volts. So this IA is equal to I basically. Next is the armature resistance, RA is equal to 0.8 ohms, and machine has 6 poles, P is equal to 6, and it is lap connected. So in case of lap winding, so the number of parallel paths is equal to number of poles, P is equal to A. So lap connected with some number of conductors, total number of conductors in the armature is 864 conductors, 864 conductors, and the flux per pole is given, the flux per pole is given phi is equal to 0.05 weber, 0.05 weber. Now what we need to calculate is that, calculate the speed, and second one is the calculate gross torque developed by the armature. See the terminology, gross torque, gross torque developed by the armature, gross torque developed by the armature, gross torque developed by the armature. So or just you should understand that this is not the final mechanical torque. So gross torque, generally here let me make some kind of slight change that, just why, because here gross mechanical torque is different, gross torque is different, just to avoid that. So I am taking this just simply mechanical torque to avoid the confusion. Just see that, is it the final shaft power or is it the armature power, that you are considering. So what torque I need, the power developed by the armature, so that I would like to take in this way. So now let me see here what data is given, based on that we can interpret. So now can I write here V is given, I is given. So can I write generalized relationship with EB? Here EB is generated, EB. So now what can I write? So this relationship as EB is equal to back EMF is equal to applied voltage minus IARA. So this expression you should carefully write by using KVL. So applied voltage is how much? 480 minus IA is how much? What is the IA? IA is equal to 110 into RA is 0.8. So once you simplify this, just cross check it how much you will get the answer. So I hope so you will get this as armature resistance is 0.8 or okay. So this is given as 0.2, sorry, 0.2. Then if this is 0.2, just cross verify if I am wrong. So this is 458 volts. So now, so once we get EB, we know clearly that some more things, or let me write EB is equal to P Z by A into flux phi into speed. So speed in RPS. So this expression we know. So number of parallel paths, poles and number of conductors, flux per pole, everything is given. So what we need to get is speed. So this is 458, this is 1, 458 is equal to P is equal to A. So this will get cancelled. So Z is the total number of conductors, 864, 864, and what else is there? Flux per pole is 0.05 into n. So just calculate this, then how much you will get. So this, just let me tell you, just I don't know here how much is this. So 864 into 0.05, this is the speed in rps, revolutions per second. So if you want this same expression divided by 60, you will get in rpm. Now the armature torque, the armature torque TA is equal to the electromagnetic torque. This is not the net, this is gross. So just I should say here one more term here. So or let me leave that. So just think of in this way. So this is visually what it look like, the gross should add over here. So this is what the net means. Ultimately after having all the losses subtracted, the net availability is this one. So gross means it look like this amount of torque, but in reality at the shaft it may not reach to the shaft. So previously I said here gross, but that is wrong way. So let us take the gross term over here and net term over here. This is the net torque developed, this is the gross torque developed. Gross torque developed is equal to armature torque or electromagnetic torque. So now this armature torque or electromagnetic torque is what the gross torque. And we said that this torque usually is equal to power divided by the angular speed, or the torque into angular speed is power. Which power? Armature power. So why armature power? I need the gross torque developed by the armature. So how much is the armature power? Armature voltage is EB, armature current is IA, that is what the power. So into 2 pi n. So if it is 60, 2 pi n, capital N by 60. So you can just work on this. EB is 458, which we already calculated. IA is, how much is IA? So IA, they had given I think 110 amperes divided by 2 pi into this small n. How much you will get? So that you substitute here. Just let me put one dotted line. Just work on this, simplify that and substitute over here. You will get some, so torque which is in, you will get torque, some torque in Newton meters. Newton meters. Okay. So with this, let me close this session. So that is difference between the motor and generator action. Just try to take your own time in understanding this concept. So this is very important. So take so sufficient time, repeat once or twice this recorded lecture and see that you can